Good morning, everybody, and welcome to our today's webinar. So-called E-Mobility is coming, but where should I be investing now? Which is a huge wording and huge headline. And we as EMAG, we are willing to give you, as our customers, the latest news out of EMAG for those potential components or machines. We means my colleague Michael Ehring, who is responsible for the project planning out of the EMAG systems, myself, Nicolas Meyer, I'm responsible for the LaserTech sales business out of the EMAG group. And Michael and myself will go through the presentation within the next hour. Before we start showing the very first slides, I want to take the chance and give you the motivation and the idea. So you will see some possibilities asking us questions on your screen, on your monitor back home, and feel free during our speech asking us the questions or at the end, and Michael and myself are trying to answer you the questions also in between. So I will later on continue by being more focused on laser and as well as heat shrink and joining solutions, but first of all, I want to hand over to Michael with your presentation.
Thank you, Nico. So also a very warm welcome from my side. And I will go through the agenda about the development of the E-Mobility. Part of the E-Mobility is the rotor shaft, the stator housing, as well as the E-drive transmission parts. And we will also have an outlook of the brake disc. So then what McKinsey is saying that 75% of the market in 2030 will be electrical cars. So means there will be a fast change from the current engine to the E-Mobility, which will be mainly the main components of these are the batteries, the e-motors, the power electronics, and so on. And this will be half of the market in 2023. As you maybe know, for example, Mercedes-Benz already stopped their developments for conventional engines. So they will focus definitely just on to go to the E-Mobility. So means what does this means in selling facts? You can see it here. The chart on the right-hand side is from the first half of 2020. So you have there a huge increase of selling of the BEVs and the PHEVs. So means this year we already have of these electrical vehicles an increase of 168%. So which is a huge increase. In Europe, we already have 40% of the market of these electrical vehicles. Worldwide, it is 6.3%. So means 2.65 million sold cars in the first half of 2021. So yeah, the focus is clear where we're going. And this picture says probably also quite a lot that you see here the red parts will be deleted out of the conventional engine, and mainly one part will be added. This is the electrical motor here with its transmission parts. So, and we will give you now the overview what EMAG can supply you there. The electrical motor have the relevant parts of the stator, the rotor, the stator housing, as well as the transmission. So EMAG focus more on the rotor, stator housing, and the transmission parts. First, As I already said, we will have a detailed look onto a rotor shaft and a rotor shaft manufacturing solution we already provided to our customers. So here we have an asynchronous motor which consists of a rotor shaft, a lamination stack, and the aluminum cage winding here. And this we see here in the market clearly that we have two different parts of designs of the rotor shaft. Means we have a solid shaft and a hollow shaft, and the solid shaft they're consisting most of one piece, and the raw parts are made of saw-off parts and formed parts. The finished part will have sometimes a running teeth or a spline or combined version of it. A hollow shaft is sometimes a one-piece solution, but there are also solutions on the market or designs on the market for multi-part, means you have 2 or 3 parts which gets together then into one rotor shaft. These are, the raw parts are pipe sections or impact extrusions and having a running teeth and a spline on the in or outside of the rotor shaft. And here in particular, we will show you a process chain of multiple piece. And we have here 2-piece solution of it. We have the upper part and the lower part as a raw part. And then we're starting with the first turning operation, turning the OD and ID of each part, going on to the second turning machine, doing the same on the rough surfaces there. Afterwards, we're going to the laser welding station. We have there a laser cleaning and joining station to prepare the welding surface and join both pieces together. Afterwards, we weld both parts together. After it's one piece, we're going to the induction heating and hardening. Then we're doing the hard turning of the rotor shaft. We're doing a spline toothing and grinding due to the tight tolerances at the end of the line, and we have a finished part handling a stacking cell in this case. So I will show you now the manufacturing line, how this looks. So we have on the left side the raw part feeding with some conveyors where the operator can bring onto the workpieces and feed them then to our track motion linear system. The track motion linear system moves the workpiece to the first operation, the op10, and at the same time he takes the finished op10 part and flip it over and brings it to the op20 machine, where it gets machined again the other side. As soon as the part is finished, the track motion system takes the part and brings it onto the conveyor you see up on the upper side. So we have here, the upper line is for workpiece A, and the 2 machines on the bottom are for workpiece B. So, and then the conveyor and its workpiece carrier brings the workpiece to our next cell of the line. We have here the LC4 laser cleaning machine, which will do the laser cleaning and joining both parts together. The gantry system brings afterwards the joint but not welded part to the ELC 160 and do the laser welding here that both parts are safely connected to each other. Afterwards, the robot or the gantry brings it to the robot. The robot feeds the LDAC Mind 1000 machine for induction hardening. And afterwards, the part is hardened. We bring the part to the conveyor. This is the connection between the upper and the down line, where we have our VTC 200 center drive machine that you can clamp the part in the middle of the OD, turn the upper part of the rotor shaft and also the lower part of it, that you have a new basis. Due to the hardening, you will have there some deforming, and now we are doing here a new centering, that the grinding machine at the end of the line have a good basis to get into the tight tolerances. The gantry system will pick the machined rotor shafts out of the VTC 200 and brings it to the Köpfer machine, where we mill our tubing onto the rotor shaft. Afterwards, as I already said, we will grind the rotor shaft on a HG 310 machine at its final tolerances. And the stacking cell at the end, the operator can easily remove finished work pieces and bring it back to the line.
Michael, may I interrupt you? I want to take the chance. I have seen there was one further question in regards to the output of that line. So can you give us also a brief overview about the output of the line?
Yes, for sure. The output on that particular line was 360,000 parts per year. So yeah, it's a good size for manufacturing line, which it makes definitely sense to have a connected line for this high volume.
So I hope that was the answer in regards to that question, but I think yes. So then I want to hand over or take the chance and continue by showing you or giving you a better overview about potential projects for rotor shaft welding. We've decided to put two different possibilities, two different machines into that presentation. And the first overview you see over here is a summary for a request for a laser welding machine, which has to be focused on truck rotor shafts as well as passenger car rotor shafts. And you can simply see the overview over here. So the request was having a machine which is having the possibility up to 1,000 millimeter length as well as 100 millimeter in diameter. And the request was also having a joining solution or joining function in the machine, including preheating, post-heating, and due to the pretty tough or tight tolerances in two single rotor shaft components, we have also implemented a sensoric system, which is checking the position right before we start welding. I want to continue with this function because it's, let's say, a very, very unique and important function in a laser welding machine for rotor shafts. We have designed and developed a system so-called EC seam, which means EMAG controls the seam. So we are having a seam detection. This seam detection camera is mounted next to the optic, and we are going to control the two different workpieces, and we are trying to find the right or middle of the weld seam. So you can simply see it on the left side. This is the diameter, which means we are checking the tolerances at the end of the day, the run out. And this information is directly forwarded to the machine, and the optic is having an NC controlled axis, and this NC controlled axis is moving during the weld seam to be 100% sure that we are always in the middle of the two workpieces with the weld seam itself. To give you a better understanding or overview how such a system could look like, it's a video made about 2 years ago approximately. So we have already delivered that line, manually loaded. So our colleague here is loading the two single components into the line. First of all, we have started to join the two workpieces together, completely force and weight controlled. Then we move the whole slide into the machine, we start by using our EMAG LDEC equipment to preheat the workpieces with an induction coil, completely controlled. Now the workpiece is having its perfect temperature, and then we start by finding the seam position, as I previously mentioned. So now the machine knows where to weld, and the weld operation starts immediately right afterwards. Then the slide is moving out of the system to the right side. It can be then manually unloaded, and in the same time, you see it here on that picture, the left side slide is moving into the machine, so it's change in between slide left and slide right to reduce the, let's say, change over time, or the time between manually loading and unloading down to a minimum. That's a huge machine developed, I mentioned, especially also for rotor shafts for trucks as well as passenger cars. For sure, we are also having a possibility and a line which is more compact, just being focused on passenger rotor shafts. And this line is standing right now in our plant. Last evening, I walked through the company and I've seen that we are close to start with the programming of the whole system. And you can see here on the left side, we are having a conveyor system. The conveyor system is responsible for bringing in the two single parts as well as bringing out the finished part. So the handling system is picking up the two single parts, move them directly to the laser cleaning machine. The laser cleaning machine as well as the laser welding machine are having an indexing table function. So loading and unloading is in parallel to the machining time. So we start cleaning the two workpieces. After we have cleaned the workpieces, we move directly to the welding machine. And in this welding machine, we are having the same functions as in the horizontal one. So we are first of all going to press the parts together. We are going to find the seam or the position where we have to weld, and then we start welding. It's a very compact solution, and we as EMAG are having for sure in this whole line the possibility to include also the pre and the post machining lines, and in general it's a complete manufacturing system. To continue, and this is a picture I have made in our application department. On the left side you do see a weld seam. So it's a polished and cutted and polished surface. So, and on the left side, you also see the contour of the two single components. Several welded workpieces. We have also done some testings the last several weeks because there are quite a lot of new requests. And the reason why I want to share this slide with you is for sure at the end, our focus is on delivering and realizing whole systems, machines, but it always starts with the very first step. And one step is to figure out, is the design of the workpieces, let's say, weldable? And we as EMAG are able to support with those kind of questions. We can do some small series, some prototyping testings, and this is why I mentioned that slide. So feel free to forward us some requests. It's not always needed to forward an RFQ for a machine. We are also lucky having the first possibility of doing some testings, and this is the reason why I share this slide with you, and I want to motivate you. If there are some requests, feel free. If we continue and just imagine the rotor shaft has been completely manufactured and is finished, then we continue to bring the rotor shaft together with the blank sheet metal package. Here you do see the bill of process for the assembly line. After assembly, we are having several functions like the turning, the post-process measurement, as well as balancing. And afterwards, we can take the finished parts into a stacking cell or whatever is needed. Myself, I want to bring out now some more focus into the assembly line. So the assembly line itself is a system which is more focused on bringing the two parts together. You can see on the left downside there is an interface for the turning machine. So we as EMAG have already realized that project, and it's a huge line with pre and post machining processes as well. And here the interface is later on a conveyor system with pallets, and we have been focused on this function in a more detailed way. So our responsibility was to preheat the blank sheet metal package, bring the rotor shaft together with the blank sheet metal package, which means to join them in a time of 50 seconds. And to give you a better overview, here we have used some fixtures instead of the conveyor system, which is implemented later on. We put the blank sheet metal package into the fixture for the preheating function. So we are also using the EMAG LDEC equipment to preheat the parts with induction. In parallel, the robot is picking up the rotor shaft, moves it into the fixture of the joining position. So we move it underneath to be sure that now the blank sheet metal can be positioned in the very right way. And then the NC axis is moving underneath the joining punch socket. So now here we are having an fixture, and the rotor shaft is now pressed into the blank sheet metal from underneath through the blank sheet metal package. And at the end, that was it to bring those two parts together. And then we or the robot moves the part out and then back onto the conveyor system. After we have joined the parts together, as I mentioned it in the bill of process, we are having the post machining, and I want to take the chance and hand over to Michael again.
So as you can see here, we have the turning operation in the video. So we're doing the pre-machining with a conventional turning. And afterwards, we're doing it with our scroll-free solution. Means we're having this tool here, which you currently see on the video. And you can compare both datas on this table here. And underneath here, it is clearly to see that the scroll-free turning gives you quite a lot of benefits here. Means the surface itself is absolutely fantastic for turning. We have here a surface and the scrolling depth is also very good, which is important for a cast rotor here. Also the waveness is very important for these workpieces. The scroll-free turning is has the benefit out of the tolerances we can achieve, but also you have there a very good tool life. And the tool life itself is important, probably not here for this sheet metal package, but usually we use this turning process also for hard turning parts. And here it is more important to have or increase the tool life of its tool, which means you have a higher outcome, a higher output in your manufacturing system. So, and as we all know, so electrical drive is absolutely, the noise level is absolutely minimum. That means all the parts around needs to be in a very, very good condition, and therefore it's also necessary to have all the gears and the teeth needs to be grinded very, very good, that you do not recognize all these noises in your car. Currently, the conventional engine, you hear the motor running, but not the teeth going into another teeth. But here, with the convention or with the E-motor, it is completely different. Means we have here the solution of grinding these gears, and also, which is important, the running surfaces for the rotor shafts. And here we have our EMAG and potentially G250 high-speed machine, and you can see it in the video how the grinding process will run. In this example, for sure, running without coolant to demonstrate how it will work. And just a little hint for some designers, if they are looking today, it's important to have here some free space that we can run out with our grinding wheel for that we do not have interference on the shoulder for a crash or something like that, and that it's possible to machine the teething perfectly. So here you can see the machine. We have there 2 spindles in. Do you see the range of what kind of wheels we can bring onto the machine? And high speed means in this case that we can run the grinding head by up to 20,000 RPMs.
Michael, just one more interruption before we continue with the next line item. There was a previous question in regards to how long was the preheating time for the cast rotor. I think that's a question to my direction. So the preheating time for the blank sheet metal package is approximately 70 seconds. So if we, well, as I've presented, we are having a cycle time for the assembly line of approximately 50 seconds, which means 70 seconds preheating time, and this is why we decided to implement 2 preheating stations, and therefore we meet the cycle time requirements. And it was an induction coil which was developed for the inner as well as for the outer diameter in parallel, so we are having a chance to bring in the heat in a very homogeneous way, and yeah, the answer is 70 seconds.
Okay, thanks, Nico. So now we will move to machining starter housings, and one project we already implemented to our customer was a aluminium housing here with an outer diameter of 260 and a length of 280 millimeters. And the requirements there was surface of RZ12 down to RZ6.3. The diameter tolerances were from 45 microns up to 200 microns, and eccentricity 80 microns, and the roundness 60 microns. So for this big part, we have a solution for our EMAG Cheryl VDZ 420 XL machine. You can see here in the picture the version without the guarding. So to bring it a bit closer to you, we have here the conveyor, which brings the workpiece in the back of the machine, where the NC loading gantry can take the workpiece onto the NC rotary table. And this rotary table brings the workpiece to the working area on the left side. So it means we have here 2 working areas, one on the left and one on the right side. To have there a combined operation means left op 10, left on the right side op 20. So after all the machining, the parts go out, and we have here the moving column and the spindle, and the unit can move in all 3 directions, and which is absolutely unique on the market. We have the y-axis with plus minus 140 millimeters of movement, which gives you a good range of flexibility to machine your parts. And on our video now, I would like to show you how this was implemented. So the workpiece was loaded here in our facility by hand. You can do this also by robot or gantry, what else. And then the gantry loads the part onto the rotary table, which moves then to the op 10 working area, and the workpiece gets clamped, set the 0 points, and the operation for the op 10 starts to machine the parts with all necessary features. That we have the pre-machining here for clamping also on the op 20. Afterwards, the part goes back to the rotary table, and the rotary table moves to the middle. The gantry grips the part and flips it upside down, and this is on a separate position to avoid that swarves and coolant goes onto the workpiece carrier on the rotary table for it. And now we're clamping on the OD, So the reference was machined before on the OP10 working area, and now we're doing the machining here for OP20. So we can do their turning and drilling, milling, what everything is needed, and yeah, for the workpieces. We have the probe as well to check if the part is in good quality, and afterwards we bring the part out of the machine, going back to the workpiece carrier, and it goes to the next process for unloading or for what else is needed here.
And here also, Michael, one additional question in regards to, as I understood, additional functions in the machine. Is it possible to add future functions in the VDZ420?
So let me go back to this slide here. And as far as I understand, the question is add further functions. So as you can see here on the working area, we have here the revolver. And here probably you may see that we have here also milling spindle, which can be vertical or horizontal. And which is also quite impressive. We can add here HSK 63 milling spindle, means we can bring here a good milling process with a high torque. It's also possible to increase the x-axis of the gantry here to add some additional functions at the end of the machine. For example, a blow-off station, a brushing station, a PPM to measure the parts in a more complex way as we did it in the video on the probe. So there are quite few functions here to add in this machine. Hopefully the question was answered.
Good.
Yeah. So
thank you.
Then going to the eDrive transmission parts. Nico, so it's a big part for you.
Thank you very much, Michael. We decided to show you a very nice Porsche Taycan, not because it's a very nice Porsche Taycan, because it is having a very interesting electromotor underneath, or on the right side you do see the picture. And the idea from our perspective was to share also some potentials out of electromotors. We as EMAG have already realized the lines for those two mentioned parts, for the differential as well as for the intermediate shaft. And both parts are having, let's say, tremendous and very extreme high quality expectations or requests. As Michael already mentioned, the noise in an electronic, in an electro car is much more different compared to a combustion engine. So first of all, the noise and as well as the torque. So the torque is much more higher compared to a combustion engine. And this is why the expectations into such kind of workpieces are somehow different. Nevertheless, we are very well aware of those workpieces because they are also assembled in typical combustion engine transmissions, and therefore we decided to continue showing also some potential out of EMAG for those lines. And before I start showing you the two differential as well as the intermediate shaft lines for laser welding, I want to again hand over to Michael to start with the pre-machining of the differential cast components.
Exactly. As Nico said, we need to machine the parts before we can join and weld them. So you see here an example of a manufacturing line for those differential part housings. So you see here again our drag motion system, which connect each operation to each other by transporting the rough and finished parts. See here the operation, the turning operation at OP10 to machine all necessary features, as well as preparing the clamping surface for the OP20. The drag motion takes the finished part, brings it onto the shuttle. The shuttle moves back to the machine and the spindle picks it up from there. And we're going back into the working area and having again the next side machining. And the drag motion takes the part, brings it to our VSC 250 DD machine, which is special with also a horizontal milling spindle, which you can see here on the right-hand side. Have here the machining and drilling of all these parts. Inner turning, which is, yeah, nice to see how the tool comes into the workpiece. And having here, yeah, that you get an idea of how to machine that part and what is possible to machine on EMAG machines. Yeah, it's not just easy turning we're doing. Yeah, some complicated stuff as well. And I think you will find there a good partner in us. So in the last operation in this machine, and then the workpiece going out. The drag motion grips the part again, brings it to a blow-off station on a rotary table that the part is perfectly cleaned. And now we are doing a 100% measuring on a separate ppm to check all features. And as long as the part is good, we're going onto a conveyor and bring the part out of the line. So however this would like to look, you can connect this automatically by robot, by gantry, by a conveyor system, or you have there the operators which will pick the parts in some boxes and bring it by hand to somewhere. So we have there the possibility to integrate there anything what is needed and what is requested. So, and as Nico said, now joining those parts together, and he will give you an overview how this will work.
Thank you, Michael. So somewhere means you can directly continue by bringing the work pieces together, so the gear as well as the differential housing. And on this video and this example, you can directly see how those Porsche Taycans differentials have been laser welded. So we first of all start with the laser cleaning operation. So we put the two single parts, which are quite heavy for this special project, into the laser cleaning machine. On the left upper side, you see there is also a control checking system during the cleaning process. So we are going to clean both workpieces with a scanner optic. So the workpiece is moving and the optic is fixed. So we can be sure that both parts have been cleaned before we start pressing the parts together. Such kind of components need to have an additional separate pressing functions due to the fact that the force to bring the two parts together is pretty high, somehow up to 200 kilonewtons. So it's also force and way or path controlled. And then after pressing the parts together, we move it directly to the laser welding machine, which is having a chuck underneath. And here we bring the parts underneath the counter bearing, so-called, and then we start welding, in that case with filler wire and with shield gas. And also here the workpiece has been turned, the optic is fixed, and then we are moving the workpiece out of the system. And at the end, it always depends on our customers' expectations or requests how to continue or proceed. So sometimes, or pretty much very often, we are having brushing units after the laser cleaning station to be sure that there are no spatters on the welding surface, as well as ultrasonic testing equipment, which is also developed by EMAG software as well as hardware. So there are quite a lot of possibilities. And as always, I ask you as our customers to give us to fulfill your requirements. To continue, and this is, we decided to show the whole line. That's the second workpiece assembled in this Porsche Taycan electromotor. And we start also pretty much the same as for the differential. So we unload the workpieces from the conveyor system. Here we as EMAG have delivered a fully running system. So everything was up to our responsibility. So we start first of all to clean up the workpieces. Here, same as or similar as for the differential. Workpiece is turning, optic is fixed, the scanner optic is cleaning up the surface where we are first of all joining and then welding the parts. And here the first handling is picking up now the two single components and move those two ones onto a fixture. It's a kind of slide between handling number 1 and handling number 2. And in between, we have put the pressing function into the line, which is also up to 200 kilonewtons pressing force. And due to the tremendous high quality requests, as well as because of the material, we have implemented an induction preheating station. Here you see the induction coil also for inner as well as outer diameter to bring in an homogeneous temperature into the workpiece, so it is also turning. And after we have finally received the defined temperature, we move the workpiece also into the chuck of the welding machine. Here you can see it. Now we clamp the workpiece pretty accurate, and then we move it underneath again the counter bearing. And here you can see you cannot see the workpiece. We have just opened the area where we are welding the parts together. Also, the welding process itself is also monitored, as you can see on the right side. And the workpiece was turning. We put it on the laser seam itself. And because just the laser seam was open during the process, we have implemented a brushing system, which is brushing the laser welded surface to be sure that there are no spatters on the surface. And the second additional function to check the quality of the welded part is a ultrasonic testing equipment. Here, first of all, we press it up to be sure that we are in a repeatable position, and then we start turning and using the ultrasonic testing equipment to look into the weld seam to be sure that there are no cracks or blowouts. So it's a typical 100% measurement after we have welded the workpieces, and this is giving our customers the insurance that the quality is as good as they expect. I have seen a further question during my presentation or during the video. There is one question: which power has the laser or the cleaning laser? We as EMAG decided to use a 200 watt pulsed laser. So it is combined with a scanner optic, and we decided not to use a lower powered laser or to use, for example, also a marking laser instead, because we are convinced that the quality expectations at the end are just fitting with a higher powered laser, and this is why we decided a 200 watt pulsed laser. The next two slides are more or less, from our perspective, the idea to give you some news out of EMAG in regards to laser coated brake discs. And we decided to have an additional and separate webinar pretty soon in November. Why do I mention that? Why is EMAG being focused on coating of brake discs? The answer is pretty simple. Because of the expectations, government rules in regards to reduction of the fine dust emissions, and to laser coat the brake disc is one of the answers. So it is first of all a rear resistance as well as a corrosion protection, and we as EMAG are convinced that this is one of the answers to meet the future environmental regulations. And for sure, there are also other possibilities to reduce that by using other systems, but coated brake disc will be one of the answers. So what are we doing? And this shows, or is shown on the next slide. So a typical bill of process previously was also a very nice EMAG turning line. So we have had OP10 and OP20 for turning. We continued by fine turning as well as drilling. In between, there is a verify or checking function. And what we have done is we have added the function coating and finishing. And coating means we first of all, there are some checking functions included as well. So DMC reading, we are having a weighing function before and afterwards to, let's say, an additional monitoring possibility to check the weight of the powder we have brought onto the surface. And the laser metal deposition, so-called LMD coating, is a function which we're using to bring on, first of all, an stainless steel powder onto the brake disc surface to be sure that it is a kind of anti-corrosion surface, so that the brake disc behind will not rust. And then we put a second layer onto it, and the second layer is a kind of powder with stainless steel and carbides inside, and the carbide content is approximately 30% to achieve the hardened layer on the brake disc. And this is realized on both sides. And important to mention is that after we have finished the coating, we directly forward the workpieces, the brake discs, into the EMAG finishing line. And here we are going to hone and especially grind the surface. So grinding and laser metal deposition, so coating, are, let's say, talking to each other. There are defined interfaces to be sure that we are not losing time and at the end tolerances. And if those two lines are combined, and this is what EMAG is willing to offer in general, then you at the end are having a much more higher outcome. And that's always the goal for such kind of lines. Just 2 slides for the brake disc coatings. Again, we are having a more detailed webinar at the beginning of November, which is the 9th of November. And I really want to motivate you to join also for this webinar, because here we are really going into, let's say, into more details, more deeper, to show you the motivation behind, to show you more details, what kind of powders we are using, how does for example, a serial machine looks like. For sure, we are having the possibility to do some testings in our application lab as well, to start by doing some prototypes before we talk about mass production and so on. And all of those information will be shared on the 9th of November. To continue, we are having further webinars at the beginning of January as well as February. One is the multi-piece, including the welding of the machining for the rotor shaft. We are having a webinar for manufacturing solutions for starter housings, as well as in February, E-Moblity transmission components. As I see, we are somehow a little bit before our schedule, right?
It means enough time to ask any questions. So do not hesitate to ask him.
So there's one additional question. What is the current lead time for a fully automated line, and what will be done once the market requirements will be much more higher than now? I think it was 2 questions.
Yeah.
Talking about lead time from the current situation, I would say approximately between 12 and 14 months. Correct me when I'm wrong, but I think that's
something like that. That's exactly means we're building up the complete system at our facility, that we are sure as soon as we go on the customer's shop floor that everything will run as good as possible, and that the customer can have their SOP as soon as possible. So this is our goal. Therefore, 12 to 14 months depends on how big the line is and how complicated. Regarding what the market requirements will be much higher than now. If we will know something like that, we can have there some spare space. Means in the line we can have a spare space for a turning machine, a grinding machine, what else? Or if it comes double or something like that, we will copy the line to bring it up. And also it is possible to do their increase it step by step, means have a full line and have the half of the full line, and then when another increase should come, we can bring in the other machines. This is how we usually act there.
You said that the coating brake disc is one of the brake disc solutions to meet the environmental requirements. What other solutions are there? Well, first of all, the recuperation of an electromotor is having some positive influence into the braking systems itself. It also somehow depends how huge a car is or not. We are having an additional way of braking the cars, and that's an
drum.
Now I struggle with the English word.
A drum brake?
Yeah, Bremstrommel. So thanks, Michael. It's a drum brake, and therefore our OEM customers are using a drum brake to collect the dust in this drum, and during a service period of time, they are exhausting this fine dust during the service operation. So there are several answers, and yeah, drum brake is one of them, recuperation is one of the answers. And from our perspective, and I'm pretty convinced that this will be coming more faster than we are expecting right now, due to, and it somehow depends on the EU regulations, that it will increase in regards to co-coating or co-coated brake discs. No further questions so far?
So one question from my side, Nico, regarding the laser welding. So conventional welding is by wire. You told us that on the differential that you have there also on wire. How you do that with the rotor shaft?